All right, two things I want to tell you before I start. The first is explanation for why I'm using this. I don't particularly like the computer, but I did some damage to my shoulder, and I'm a little bit concerned that it will not last for 2 hours, so I decided to put basically a Blackboard talk on the computer, so it is as complete as it would be if it were on the Blackboard. The other thing is I've endeavored, very hard effort, to rid the talk of all ideology, all salesmanship, and that sort of thing. My own feeling is the subject speaks for itself, and if you're not working on eternal inflation, you're a blooming idiot, and I can't help you. All right. My talk really is a technical talk. It's a talk about how, in a sense, it's a talk about how I learned what some people in eternal inflation, people like Alan Guth, Raphael Busso, are thinking about and how they put things together into a package. The package that I'm going to put them into is a very mathematically precise model. It's extremely precise. It's, of course, anything that's that precise does suffer from being a little bit unrealistic, but I think it turned out to be less unrealistic than we thought when we started. We, incidentally, mean Steve Schenker, myself, Douglas Stanford at Stanford, and Daniel Harlow. And we started this project not realizing just how close, with the proper interpretation, just how close it really was to possibly what could be the real thing, real eternal inflation. And I'm going to show you how it works. I'm going to take you through details. I'm going to take you through detailed computations. They're not hard. They are precise. They're very easy. And what we're going to be interested in is some applications of this construction. The applications are not applications to new things which we discovered. They're applications to showing you how you can think about some of the things that Busso and other people have been putting together in a simple, compact model. Okay, let's begin with a non-ideological statement of why one is interested in eternal inflation, what it's about. Eternal inflation is a very, very different phenomena, very, very different in its goals, in its techniques, in its scales than ordinary inflation. So let me start by assuming, of course this is something we could get ideological about, but I'd rather not, just by assumption. There exists a complicated landscape of some sort, and for the moment I'm going to assume that this landscape is all de Sitter. We'll come back to that because we're going to find we need to worry about more general kinds of things. So by de Sitter, I simply mean that all of the minima have positive vacuum energy. All right, now ordinary inflation has to do, or well, let's forget ordinary inflation, just ordinary cosmology, ordinary physics. Ordinary physics has to do with what takes place in the immediate vicinity of one of these minima. In fact, cosmology, I should have put a little inflection point in here. A little small inflection point would have captured slow roll ordinary inflation, but ordinary cosmology has to do with a roll from some inflationary plateau down to our current minimum, down to our current cosmological constant minimum, and basically everything of ordinary cosmology takes place in that roll from here to here, and that's it. That's all of it. That's all of the observable universe. That's all that we could ever hope to directly access. And the time scales for it, well, first of all, the distance scales are horizon size. The size of the landscape that's important is basically n equals 1 unit, namely the particular vacuum you're interested in. Incidentally, the n-axis here represents the different possible minima. Imagine ordering them. Of course, they're not ordered by a single field, but n stands for which, and I'll call it the color. I'll call it the color of the vacuum. Okay, so ordinary inflation has to do with relatively small time scales of, not ordinary inflation, ordinary cosmology. Everything of interest will have taken place by 1 trillion years. More than 1 trillion years, and everything will have thermalized to a attractor behavior, and that attractor behavior is just ordinary thermal equilibrium of this particular de Sitter space. Again, 1 trillion years is a time scale. Eternal inflation is a totally different mechanism, and it's a mechanism that, as I said, has different goals and entirely different time scales. I was amused that the same picture was on Herman's screen yesterday, and for the same reason, it was talking about time scales. But I'm talking about time scales not associated with our current patch, but with the entire landscape. How long does it take, by tunnelings, up transitions, down transitions, the whole works, how long does it take, first of all, to tunnel from one minimum to the other? And second of all, how long does it take more generally to populate this whole thing and create the kind of equilibrium between up and down transitions, which will populate this whole thing with some statistical probabilities that are also a kind of fixed point, or also a kind of attractor behavior, sort of the ultimate attractor behavior? And the answer to that question is huge time scales. Time scales of order e to the entropy, and probably entropy of the maximally entropic de Sitter space here. E to the 10 to the 120.
Lenny?
Yeah. No ideology.
Question. In your terminology, does eternal inflation require a landscape? I mean, even if you have one...
No, that's a good point. No, that's a very good point. We already know that we probably live in a world with eternal inflation just from the fact that we have a cosmological constant, space is very flat. We know the universe is much bigger than one horizon size. So many of the things I'm going to say really just have to do with the fact that there are many causal patches. And I think we know that we live in a world with many causal patches. And that way we already know that we live in a world that's a multiverse. If what you mean by a multiverse is that it contains separate disconnected causal patches. And I think we know that. So the things I'm going to talk about could be applied to that, but they'd be kind of trivial if there was only one. They'd be too trivial to be interesting. Okay, now, of course, you have every right in the world to be skeptical about any kind of talk about such enormously large time scales. And I would say, in defense of these time scales, number one, they simply are the time scales of eternal inflation. There's not much point in talking about eternal inflation unless you're willing to open up your mind and be, at least temporarily, say, I'm willing to think about time scales that long. Okay. Otherwise, I think eternal inflation becomes pointless, or at least it doesn't have any bite at all. So I will ask you then to open your mind, keep your mind open about such time scales. The model that I'm going to talk about is what we don't have a good name for it. Originally we called it the cellular model. Now we call it the tree model. But it's a mathematical model which surprisingly did exhibit essentially everything that I know about eternal inflation in a form which is very simply and rather beautifully, but I take that back, forget beautifully, that's a salesmanship thing, packaged. Okay? So here's what it is. Instead of a continuous space-time, imagine a tree. And a tree, I mean a technical tree. A tree that begins at a root. For the moment, imagine that it begins at a root. The root will be labeled point, just point, that's all. And it continues upward. It could be a tree which branches p times at each node. P stands for prime. It doesn't have to be prime. But I'm going to take it to be a tree that branches twice, just for simplicity. If the number is prime, it has some particularly simple mathematical structure to it. It doesn't have to be prime. And it doesn't have to be 2, but it's, for obvious reasons, it's easy to draw 2. The results don't depend on this number p. They're rather insensitive to it. And there's a time variable. The time variable in this case runs in integers. It runs from integers from one branch to the other. From one branch, u equals 0, u equals 1, u equals 2, u equals 3. And it obviously exponentially proliferates. So that's the beginning, exponentially proliferating populations. It will have that feature. Each link here can first of all be labeled in the following way. This is the p-adic way of labeling things. P-adic way of labeling things is to introduce a new number system. Now this is not going to get very technical. The new number system begins with point on the right and just goes on and on forever. Ordinary number systems terminate. This number system goes on and on forever. It may just contain an infinite number of zeros, or it may not contain an infinite number of zeros. It may be repetitive. It may not be repetitive. And this set of numbers, this number system, labels the endpoints of the tree. Now, how does it label the tree? It labels a tree in the following way. You start at point. You go up to the left. There's no meaning to the left. It's just the binary decision. Which branch of the tree do you go on? You call one of them 0 point, and the other one 1 point. Each time you go up 1, you add another digit to the left, and either a 0 or 1. If it's a 0, you put it on the left. If it's a 1, you put it on the right. And so you decorate the entire tree with a collection of numbers, and those numbers label the edges of the tree. Technical term is edges and nodes. Okay, so that's a number system, and the infinite chain of them labels the endpoints. The endpoints, you could call it future infinity, the analog of future infinity in de Sitter space. The analog of future infinity in de Sitter space is labeled by the infinite strings like that, and those are called the p-adic numbers. They're a p-adic number system. You can do algebra with it. You can add them. You can do a lot of mathematics with them. Just keep in mind that there exists this p-adic number system up here which labels the points at the ends of the string. Not ends of the string, ends of the universe. Excuse me, ends of the multiverse. Okay, those are the p-adic numbers in P. They begin at point and go on and on. This is a model of global de Sitter space, which starts at the waist of the de Sitter space with some initial condition and then continues to proliferate and explode. There's also a mathematical model that can represent the flat slicing of de Sitter space, in other words, infinite open slicing, and it's the p-adic numbers, not the p-adic integers, but the p-adic numbers, and the p-adic numbers just continue backward into the past with more and more numbers to the right of the one. It just forms an infinite Cayley tree. It forms an infinite Cayley tree that just goes down and down into the remote past. And that's a model that has similarities with the flat slicing. I'll often use it because I'm mainly interested in what goes on very late, and for that it doesn't matter. Okay, so there's the time. Time is called U. It's analogous to proper time, right? And that's the setup. That's the basic setup, replacing the multiverse. Okay, now there's some notions of causal structure. Causal structure, I think, is all important to what the causal structure of a space-time is. And I'll just illustrate it by a couple of examples. First of all, there's a causal relation. A less than B, that means A is in the past of B, and it means that A can send a message to B. Sending a message will mean along the links of the tree. All right? So here A is in the causal past of B. A point over here would not be in the causal past of B. Okay? So these 2 points are related by causality in the same way as points in de Sitter space. There's a notion of a causal future of a point. Here's a point. Its causal future is everything that it can send messages to. That is not the whole of future infinity, obviously, for the same reason that it wouldn't be the whole of de Sitter space. There's also the notion of the causal past. The causal past is everything that can send messages to that point. So that's the causal past. There's also a notion of causal diamond. If you pick 2 points, it's the intersection of the causal past and the causal future. And finally, all important, the notion of the causal patch of a point at infinity. A point at infinity, which means a p-adic number, has, or a 2-adic number in our case, a p-adic number has an infinite trajectory running backward that represents all of these sequence of links that went into it. That p-adic point has a causal patch, which is all of the things which can influence it, if you like. All right, so these things are quite similar. Oh, incidentally, if you follow the tree, things fall out of causal contact, exactly as in, or in a very similar way to the way they do in de Sitter space or in a multiverse. All right. Yes? I'm deaf, so give me a...
Is this supposed to be one
Oh, I know you.
one single global de Sitter space? This is a model of de Sitter.
At the moment, this is a model of a global de Sitter space, but possibly including equilibrium between all the different minima. As far as I'm concerned, the real exact notion of de Sitter space really means the equilibrium that's set up between all these minimum. But of course, that takes a long time to happen, so there's an approximate notion of being in one of the minima. But we'll discuss that in a minute.
So there's one thing which is very unlike de Sitter space in your discrete model, which is that the causal past of an event or a node is very different from the causal future. So the causal past is just one chain, right?
You should think of this. You should think of this as a model for half of de Sitter space, the future half of the hyperboloid. In that sense, this is very similar. You trace back until you get to the root. At the root, there's only one causal patch. That's like tracing back in de Sitter space till you get to the waist. And in the waist, everything is within one patch. So it's quite close.
Lenny?
Yeah.
Is this connected with the notion of causal sets at all?
I suppose it is. I suppose it is, but I'm not going to make particular use of it. I know what you're talking about. But I assumed that the notion of causal structure of a space is common. I hope I'm getting it right.
Sorkin, Dalker, they have discrete points everywhere, only causal relations.
Yeah.
Yes.
Yeah, it's connected. It's certainly connected with that. Yeah.
So the other thing that one might ask, about is the notion of sort of continuity at Scri Plus, which I've forgotten my p-adic numbers and whether, okay, you're going to address that?
Yeah, we're going to address it. I'm going to show you some things. I'm going to show you how close this is, but with a translation dictionary. Now, you're right. The p-adic numbers are not a continuum, and...
My specific question is, if I start at the bottom, I first go right, and then always go left, versus first going left and then always going right.
Okay, let me say what you're going to say.
Yeah.
There's too much symmetry here. There's the symmetry of permutation among all these causal patches. I think that's what you're getting at. That.
But you can address that anyway.
It's got a lot of symmetry.
Actually, it is related to that.
Of course it is. Of course it is. Okay. Now let's take the concept of bubble recreation.
So sorry, your statement was it has too much symmetry. We'll worry about that later.
Yeah.
Okay.
We'll worry about it later. Yeah. Right.
Can I just say one point?
Yes.
Just something you might be interested in, which is that this tree-like structure, this tree-like growth, appears in a model of causal set dynamics, a classical stochastic model investigated by David Rideout. And the pictures that he gets of the causal sets that come out are very much like that.
Right, that may very well be. We looked in the literature to find things like this, and we didn't there, but I would be very interested in hearing what predecessors there may be to this. Let me. I don't like to shut down conversation, but what I'll do is I'll stop every so often and say, are there any questions? For continuity purposes, try to keep some coherence to the lecture. As I said, I work pretty hard to keep it clear, but I will stop now and then. Okay, each link of this lattice should be thought of as having some color. A color means one of the minima of the landscape. So each link contains an index n, and if all the n's were the same, this would be the special case of one de Sitter space, so one minimum. That would be the special case of all the n's being the same. Now, of course, what we're going to be interested in is the population statistics of n's and m's, so it wouldn't be too interesting from that point of view if there was only one minimum. N labels a particular minimum, a particular point on the landscape, if you like. Let's talk about the notion of a bubble nucleation. I could have drawn a picture of bubble nucleation in de Sitter space, and you know what it looks like. I won't bother drawing it. If you take any point on the tree, and it's labeled with an index m, a color m, and you trace backward, you will eventually come to a point where it's no longer m, where it will be n, if you go back even further. That point is a bubble nucleation. It's the bubble nucleation of a bubble of type n, m, in a background of n. Okay? And there's a rate for it. The rate for the transition from n to m is analogous to the Coleman-DeLucia bubble nucleation process. And we'll call it gamma n m. And note the way it reads. You go from n to m. N to m, n initial, m final. And we assume it's much less than 1. I will assume it's much less than 1. Although I'm not even sure how often I've used that, but I'm going to assume it's much less than 1. If it's anywhere up near 1, you have a pretty good probability of the whole thing going plots into oh, no, not here. Forget. I was going to say something wrong. Okay. Detailed balance. Detailed balance is going to drive almost everything I say from here on. So what is detailed balance? I will motivate it by simply saying it's a property of Coleman-DeLucia instanton calculus. It says that the rate for going from n to m and the rate for going to m to n, and you can go from n to m and you can go from n to n. Up transitions and down transitions are thermodynamically allowed, but they are related by a factor of exponential of entropy. The meaning of this is that gamma mn is a symmetric matrix. A symmetric matrix equal for going from m to n and n to m times a density of states factor e to the entropy of the vacuum m. All right, the usual Hartle-Hawking or Gibbons-Hawking entropy of the local de Sitter space. That's detailed balance, with m being symmetric. Okay, let's try to move on a little bit. Now, let's go to a level on the tree, a particular time, u. And let's count up the total number of vacuums of type, or the total number of branches of type m. That means the total number of causal patches at that point of type m relative to the whole, and call that the probability definition. This is the definition of the probability that some link, some randomly chosen link, has property m, or has a landscape index m, just that ratio. And then, from the rules that I've laid down already, there is a rate equation. The rate equation tells you how these probabilities change with time. And here it is. I'll write it down once. Pn at time u plus 1, in other words, when you move up one link on the chain, is of course equal to Pn of u. If the rates were 0, that's all there would be. And then there's the possibility of leakage from n to m. N goes to m, you deplete. This is the depletion term, that's why it has a minus. Probability of n times the gamma for n going to m summed over m. But then there's the opposite, not the depletion, but the, what's the opposite of depletion? Increase, thank you. The increase, and that's you're originally in m and you go to n. So there are these two terms. This is the linear equation. There's a matrix composed out of these gammas, and it can just be written as GNM Pn. That's Pn, summed over m, of course. Summed over m. This matrix is not symmetric. It is not symmetric because the gammas are not symmetric. However, this piece of it is symmetric, and it's not only symmetric, it's diagonal. Pn, Pn, Pn. This piece is off diagonal and not symmetric. All right, so that's a good thing to keep in mind. It's not symmetric, but using detailed balance, you can symmetrize it. You can symmetrize it by a similarity transformation. Using the detailed balance, this is it, you discover that if you multiply from the left by there's a symmetric matrix, that if multiplied from the left by e to the s over 2, oh, incidentally, this s has nothing to do with this s. This s is entropy, this s is just some symmetric matrix. All right, the symmetric matrix, if multiplied from the left by a diagonal matrix and the inverse of the diagonal matrix on the right, it becomes symmetric. That's good?
Before you did that, is the sum of the rows equal 1?
Yes.
It's a doubly stochastic matrix.
Absolutely. This is extremely well known to people who do Markov chains and stuff like that. Right, absolutely, yeah. All right, so you do this trick over here. You, at the same time, do the corresponding transformation on the vectors, the p's. The factor is e to the minus sm over 2, and you define some similarity transform of the p's. And what you find is that phi obeys a stochastic equation that phi n is equal to snm phi m. That's the way you update. Nice to have symmetry, because when you have symmetry, you have orthonormal eigenvectors. And incidentally, the eigenvectors are the things which have definite scaling time dependence, or definite exponential dependence. Well, let's come back to it in a minute. As Gary said, the p's are conserved. This is some properties of the sum of the p's are conserved. The IMs are the eigenvectors of the S matrix. The eigenvalues I will call e to the minus delta I, 2 to the minus delta I, 2 to the minus delta I. In a more continuous context, I would probably call it 2e to the minus delta I. And I will call delta i's scaling dimensions. They will appear as scaling dimensions in the sense of conformal field theory soon enough. The i's and j's are orthogonal to each other. We can normalize them. I and j are orthonormal basis. And if summed over I, you get delta n m. This is trivial. The largest eigenvalue corresponds to lambda equals 1. That's the thing which doesn't evolve with time. No time dependence at all. It's an equilibrium attractor. The corresponding eigenvector will just be called 0. It's not 0, but O. O for I don't know what. And O sub m is the index structure of the vector O. It turns out to be e to the sm over 2. Just plug it into the rate equations, and you'll find out that it works. Okay. Correspondingly, since p is related to O, or p is related to the orthonormal basis by another factor of e to the sm over 2, that was the similarity transformation, you find that the probability distribution is just the good old e to the sm. In other words, the equilibrium where every microstate is equally probable. Every microstate is equally probable, e to the sm, and that's equilibrium. That's the equilibrium. Keep in mind, if it was only one point on the landscape, this would be ordinary de Sitter equilibrium. But if there are many points on the landscape, we're talking about the equilibrium that takes these ferociously long times to get established. How did I get back to here? Okay. This GMN, remember what that was? That was the matrix that went into the rate equation. Not the symmetric one, but the one which was not symmetric. That can be written. I'll use this over and over again. There's an e to the sm over 2, an e to the minus sn over 2. That's the transformation between the orthonormal basis and the mn basis. And then there's an expansion of the symmetric matrix in its eigenbasis. I sub m, I sub n times the eigenvalue of the ith vector. All right, so this is a useful representation. We will use it, but I'm now going to define a concept called the propagator. This notation was an unfortunate one. It has nothing to do with propagators of quantum field theory. I made it up, I'm responsible for it, and I apologize for it. Well, it's a bad notation. It should have been called the connector. If I had to do it again, I would call it the connector. All right, what it is it's the probability if at some point in the chain, in the U space, a edge has type R, that if you follow it through U steps, it will have probability, it will have type N. Transition from R to N over a time interval U. And this is easy. You just take the G matrix and you raise it to the uth power. Each one gives you a factor of G, and that's it. PNR reads probability at starting with R, after time U, you get to N. And that's just the uth power of G, and that's it. And it is given by the same kind of thing here, except with the eigenvalue raised to the uth power. Okay? So we will use that connector soon enough. Okay, now let's talk about equilibrium, in the equilibrium distribution, correlation functions. And by correlation functions, I mean correlation functions on future infinity. The sorts of things that by now we've gotten used to, thinking about future infinity as the seat of some kind of set of correlation functions. And, oh, I think I missed a transparency, very important transparency. I forgot all about it. Let me go back a step. Otherwise, I'm going to spring something on you, and here it is. I thought I right over here. There is a notion on a tree like this of the distance between points. It's called the p-adic distance, and it's defined in the following way. There's a very, very close correspondence with the way distance on the boundary is defined in either anti-de Sitter space or de Sitter space. Well, I won't ask you to fill in the details there, but I'll show it to you if you want to know later. Take any 2 points on the boundary, two p-adic numbers, and trace backward from each of them until the unique place where they come in causal contact. The unique node where they come in causal contact. Label that by time U intersection, U sub I. Then the distance between x1 and x2, definition of the distance, of the boundary distance, is that it's 2 to the minus ui. I will tell you what it measures. It measures how deep into the graph you have to go to find a common node, to find a common origin between them. The Sitter space is very much like this. It has the same kind of structure, and it's very useful to know that for calculating correlation functions.
Lenny?
Yeah.
Regarding distance in de Sitter space, so which distance are you referring to?
This is a definition of distance on future boundary. Mm-hmm. Okay? So it can be thought of as co-moving distance. But
if you had to do it through the bulk, do you have a natural definition of that in terms of the intrinsic bulk geometry?
Yeah. If you think in terms of conformal coordinates, you will realize that the distance between 2 points is how deep you have to go down before their backward light cones intersect. Same concept.
Another question. This has a resemblance to the master equations.
It isn't. I'm not sure what a master equation is.
The equation is a rate equation.
Yeah.
Very similar to the one you have.
Yes. Yeah. It's the sort of thing. That's right. Yeah. Absolutely.
There's a piece where you don't go.
Yeah. No.
And from that you can establish increase in entropy.
For example. Absolutely.
You just need unitarity. So if it wasn't for these...
What Ivan is saying is correct, that it is really just unitarity that's at work here. And, that's right. Good. All right, so equilibrium correlations. Correlations in the equilibrium eigenvector. All right, the first correlation function is just obvious. It's just not a correlation function, it's a one-point function. And I will just take it to be the probability, since it's independent of time in the equilibrium vector, in the attractor, just Pm, the probability, which is e to the Sm. Anywhere's on the p-adic endpoint here. One-point function is translation invariant. There is a notion of translation, incidentally, among the p-adic numbers. All right, much more interesting is the two-point function. And the two-point function is the joint probability that x and y have color m and color n. So here's how you calculate it. I'm going to show you how to calculate it. Just to think for 2 minutes and you'll realize that this is the right prescription. You go backward from x and backward from y until you find the joint place where they meet. Call that incoming edge over there R, and call the time at which they meet U intersection. Then C2, this thing over here, call it just C2 over here, is the sum over all the possible things that could be entering the common point here, times the probability that that link has color R, right? You start with a link of color R, but give it a probability PR, times the propagator to go from R to M, that's this propagator over here, and R to N. Now, incidentally, I have cut off the time. I've put a regulator in that cuts it off. As always, we're going to have to cut off times and take limits as we go to time infinity. All right, so this is what the joint probability at a future time u0 would be if an incoming link had R, then summed over the probability p sub R. And it's as simple as that. Now what we're going to do is we're going to plug in for p sub R the equilibrium distribution, and plug in for these propagators what I gave you before. You probably don't remember what I gave you before, but I will try to remind you. All right, so here it is again. PR, propagator from R to M of U naught minus UI, the late time at the end of the world, minus the intersection point, and PNR. That's all it is. PR is e to the SR in equilibrium. The propagator here has a factor e to the SM minus ESR over 2. The other propagator has a similar factor, e to the SN minus SR over 2. And then there is the piece that depends on the eigenvectors. What did I write here? IMIR. This is not imaginary part. I keep doing this. I keep thinking this is the imaginary part of something. I'm looking for the other piece. I sub m, the eigenvector I, its projection onto m. Eigenvector I, its projection onto R. R was in the past. That was the intersection point. Likewise for J. These two things correspond to the two propagators from here to here and from here to here. Okay, so let's isolate some factors. First of all, the e to the SRs cancel. Ooh, that's nice. That's good. E to the SRs cancel. I mean, I don't have to write them again. One from here and one from here cancels this one. And let's concentrate on the R dependence. There's a IR here and a JR here. And it has to be summed over R. There's nothing else with an R dependence. Sum it over R. Use the orthonormality of the IJ basis, okay, and that sets J equal to R. So there's only a sum over one eigenvector, I, and it becomes IMIN, lambda I to the minus 2U naught. I'll tell you what that is in a minute. But let's look at the UI dependence here. We have a lambda to the minus UI here, another lambda to the minus UI here, and that's all, I think. Remember the definition now of the p-adic distance, or the two-adic distance between points. The two-adic distance had to do with how deep into the graph you go until they find a common point. Well, that's exactly U sub I. With the definition that lambda is 2 to the minus the scaling dimension, this factor over here, the UI dependence here, just becomes 1 over x minus y, p-adic distance to the twice delta I. All right, where delta I, again, I remind you, is just the logarithm to the base 2 of lambda I. This looks remarkably like a conformal correlator. And it is a conformal correlator with the right interpretation, but keep in mind that this x minus y is the p-adic distance. Okay, this e to the sm over 2, e to the sn over 2 times IMIN, you can just think of that as projections from the MN basis to the IJ basis. The whole thing is diagonal in the IJ basis, And it has the structure of correlation functions between conformal fields of definite dimensionality labeled by I. Okay. That's what this looks like. Is it an accident? Well, at first we thought maybe it's an accident. So we went on and computed the 3-point function. Oh, we did go on. Let me go back. Let me go slower. If I go back, this is what the correlation functions in the IJ basis looks like. If I go back to the expression for the correlator, here it is. And I substitute in here the equilibrium eigenvector. Just the equilibrium, saturated by the equilibrium eigenvector. That contribution will just be the cluster decomposition of the 2-point function. The cluster decomposition, meaning to say it's a thing which in conformal field theory you would say saturated by the identity operator. All right, so the eigenvector I is functioning as the identity operator in a kind of conformal structure of some sort. All right, so it clusters, and that's about it. Looks like conformal field theory. Okay, so we were not convinced that this was a conformal. I shouldn't call it a conformal field theory. I have no idea if it's a field theory, but it's a conformal Fluctuations. We decided to calculate the 3-point function, see what kind of structure it has. Equally simple, almost as simple. You start again at the point which is the common ancestor of all 3 points. If you take 2 points at a pair, they'll have a common ancestor over here, let's say. And then if you look for the common ancestor with the 3rd one, it's a point R. You write down propagators times probabilities. You do the same thing, and what do you get? You get something that looks exactly like the 3-point function of a conformal field theory. For those who recognize conformal field theory correlators, here it is. And in the IJK basis, the conformal basis, it looks exactly like a conformal correlator of an I, a J, and a K at point X, Y, and Z, with the structure constant Cijk being given by taking the eigenvector In, Jn, Kn times e to the minus Sn over 2 and summing over n. That's the structure constant that you get. The interesting thing that my students recognized immediately, being much more proficient at conformal field theory than I was to ask the question, does it satisfy, what is this called, associativity? Yeah. And yes, it satisfies associativity. This is a 1-line proof following from its definition and the orthonormality of the IJKs. It satisfies associativity, or what I would call crossing symmetry. Right. There is an operator product expansion. It looks awfully much like conformal field theory.
Just one genuine question.
Yeah. Mm-hmm.
Is the only input to this theoretical input the gammas?
Yeah. Pretty much.
What?
Yeah, I think so. And the gammas, the entropies, the S's.
Oh, yes, that's right.
Right.
And the definition of the p-adic metric.
Absolutely. I mean, I think if we actually started counting inputs, it would probably be quite a lot. But yeah. Yeah. Yeah.
Gammas and the S's.
Yeah. All right. So, first of all, the 2-point function was diagonal in the index I. One can ask, what does that mean? That's certainly something that you expect in conformal field theory. But it is closely connected, first of all, to conformal symmetry, but to time symmetry, the absence of an arrow of time. In general, just scaling symmetry, pure scaling symmetry by itself, would tell you that this kind of correlator should be sums of terms with x minus y dependence, where d would be the sum of the dimension of I and j. That's about all you can get from pure scaling. Okay? If you take, in addition, conformal symmetry, in particular, the special conformal transformations which hold the 2 points x and y fixed, they have orbits which take the points from here to here, sweep them through here, one point being going backward in time, the other point going forward in time, if you like. That's the additional symmetry which tells you that they have to be diagonal. Right? So the question is, where did this extra symmetry come from? Why was the correlation function diagonal? Why does it look so much like conformal symmetry? Is there some kind of structure among the p-adic numbers which carries this kind of symmetry? And the answer is yes. I'll show you what it is. If you take the case of the sort of flat slicing, which goes backward down to minus infinity, or equivalently just look at the very late times, then the structure of these graphs is that of a Cayley graph, a Cayley tree. A Cayley tree just goes on and on forever and ever and ever in every direction. Okay. It has endpoints, the endpoints being an infinity. In other words, it has a boundary. The boundary is the p-adic numbers, the p-adic number system. It's exactly the p-adic number system. And now take 2 points on the boundary, any 2 points on the boundary, and ask, is there a symmetry which holds those 2 points fixed and sort of slides you along from one point to the other? And of course there is. It took us a little while to realize this, but just redraw this graph. Take this, call this the spine. It's nothing in particular, but call this the spine from one point to another and draw the spine vertically. And now from every, here, you emit a vertebrae or a bush. I think these are technically called bushes. And the bushes are arranged periodically in such a way that there is a symmetry which takes you from one bush to the next bush to the next bush, keeping the endpoints fixed. This is a symmetry of the tree diagram, but it's also a symmetry of the p-adic numbers. It acts on the p-adic boundary. It acts on the p-adic boundary, and I will tell you what it is. It is a group. The group is PGL2QP. It stands for projective, general, linear transformations. I forget what the 2 is. And Q sub P is the p-adic numbers, the p-adic number system. Okay? But what it is let alpha, beta, gamma, and delta be elements of QP. I've been using P equals 2, of course, but it could be any P. Let them be elements of Q sub P and take the transformations. All the algebra here is done as p-adic algebra. It's a horrible experience to try to multiply or add or do a p-adic numbers. It's crazy, but still, you can do it. And this is the transformation. Looks like conformal transformation. This is the source. This is the ultimate source of the conformal structure here. Now, there is one point that the symmetry that I've described is a symmetry of undirected trees. Undirected trees means that the links have no directionality to them. Why does it apply to trees in which, by definition, each link has a forward direction in time? The answer is detailed balance. Without the detailed balance, this would not be a symmetry. So the detailed balance, which is time symmetry, forward, backward, of the equilibrium eigenvector. The time symmetry of the equilibrium eigenvector is the ultimate source, or one of the sources of the of what's going on here.
So that means applies to equilibrium correlation functions.
Yeah, equilibrium correlation. Yeah, right. If we took one of the transients, of course, it would not be true. Right. Okay, let me jump to a causal patch description. We are, of course, in asking a question about arrow of time, I'm not really interested in the whole multiverse. The whole multiverse looks like it has an arrow of time. It just gets bigger and bigger and bigger. But I'm interested in a single causal patch. What's going on? So here's a causal patch that ends up somewhere at infinity. It emits more causal patches and so forth, the tree structure. And let me ask the following question. First, given that a link at time t has vacuum type m, what is the probability that at u plus 1 it has vacuum type n to n? That, of course, and this is a conditional probability that at time u plus 1 the vacuum type is n, given that at time u, a little earlier, it's vacuum type M. And obviously the answer is gamma Mn, the transition probability for M to go to N. Okay, that's clear.
Assuming you've traced some specific line that you're...
It doesn't matter which line you trace. Okay. They're all the same.
You have traced a line because you're ignoring the other.
Yeah, that's right. We traced the line. We traced the line, but any line, they're all the same. Okay, now, what about the opposite? Given that at time U, the vacuum type is M, what was the vacuum type at U minus 1? This is the conditional probability that you know that at time U, you have M. What's the previous color? What's the probability of the previous color? It's more or less like the following question. Supposing there was a gas vessel over there in which you could compress a lot of gas, keep all the gas in, and then let it out. Now, at a particular time, I look at the room and I find a lot of molecules up somewhere near the corner here. I ask you, what's the probability that they all came out of the gas cylinder? And you'll calculate some probability for me that they recently came out of the gas cylinder, and you get some number. Okay. I could then ask you the opposite question. I could ask you, what's the probability, given the current configuration right now, what's the probability that the same amount of time into the past they were in the container up there? This is highly unintuitive to me personally, but the answer is the same. The probability that the molecules came out and were found in a certain place is exactly the same in thermal equilibrium, as the probability that they were in the box in the past. No, that they will be in the box in the past. Even though the box is a small entropy thing, that's a property of equilibrium. That's also a property called not having an arrow of time. So let's check it. Let's check it and see what the probability is at time U minus 1 that the vacuum type is N, given at a later time it's U. And I loved doing this because I got to use Bayes' rule for the second time in my life. How many people have ever used Bayes' rule in calculating something? Oh, I know you have. You probably invented Bayes' rule. He's my student, too. Okay, Bayes' rule. What Bayes' rule says, don't ask me how you prove it. You can ask me later, but not now. It says that the probability we're interested in is the probability, the conditional probability for turning it around, I just interchanged initial and final, multiplied by Pn of U minus 1, the total probability of the final thing here, divided by the probability of the thing over here. I don't know how to use the right words. If you plug this in, oh, look at this now. Pm, M now is earlier. No, N is earlier than M here. N is earlier than M. So here we know what to do. This is just gamma N goes to M for this piece. N goes to M. But we have to multiply it by this ratio. And this ratio is just e to the Sn over e to the Sm. And it is just gamma N M. It just interchanges M and N here. That's the nature of detailed balance. Detailed balance just tells you that the probabilities have this perverse symmetry, which is equivalent to saying there's an arrow of time. There is no arrow of time, excuse me. This is Boltzmann's nightmare. We'll come to Boltzmann's nightmare in a few seconds, but let's make a lesson. Lesson. Conformal attractor and time symmetry. I'm not going to call it a conformal field theory, but a conformal attractor and time symmetry have a common origin in detailed balance. Now, I believe this is true. This has nothing really to do with trees. I think it's much more general. The tree is just a structure in which we can exhibit it in a completely solvable manner. Detailed balance, conformal symmetry, conformal attractor have the same origin. An arrow of time must mean no conformal fixed point. Okay.
This stable conformal fixed point.
What's that?
Or no stable conformal fixed point?
Yeah, I always get confused about that. No, I don't think it means that. But you might think what that means is it's a flow from one fixed point to another. That's not the right picture. That is definitely not the right picture. Okay, to go on, anybody want to take a 5-minute break? How much more time do I have? Another hour, roughly? Who's the boss?
Joan. You can keep going, yes. I mean, we No. Not up to the time scales that you are talking.
No.
I mean, we have the room for 2 hours, so you have more.
So I've been going at it for an hour, roughly.
You've gone for 1 hour.
Would people like to take a break?
How much more time do you think you need to finish this?
How much do you need?
Oh, I'll use most of the hour.
Another hour.
But maybe less. Probably less. But that's an impolite question. You could have asked it another way. You could have said, Susskind, how big is your bladder? All right, so we keep going?
Keep going.
Arrow of time. So what then do we need to have an arrow of time? Okay, well, Penrose's answer is that you need a low S initial condition. I think in some sense that's certainly true. You need to have in the past some lower entropy to be able to flow to higher entropy. But in some deeper, broader sense, I will tell you that this is neither necessary nor sufficient. And I am thinking, here we are really now beginning to talk about these enormously large timescales. Right? So here we're buying in. I'm buying into the idea that there are such long timescales and that they're meaningful, and that these equilibria are set up, these attractors are set up over very long times. Okay, so let me just give you a cartoon of Boltzmann's nightmare. This it was expressed by Boltzmann. More recently, it was expressed by myself, Kleban, and Dyson. And it's sometimes called the problem of Boltzmann branes. I don't like thinking about it as Boltzmann branes. I like to think about it as Boltzmann fluctuations, the problem of Boltzmann fluctuations. So just as a cartoon, imagine a phase space that consists of the entire phase space of eternal inflation. Over here in a tiny, tiny corner, and I drew this, I meant to draw it much smaller, in a tiny, tiny corner is a very low entropy starting point. It could be an inflating starting point with a vacuum energy which is much larger than our vacuum energy, and therefore an entropy which is much smaller than our entropy. Okay, here's us over here, the world as it looks more or less today, maybe with some tolerances, not quite exactly the same, some phase space over here. In this part of the phase space over here, everything is normal. Dinosaur bones are buried deeper than monkey bones, and human bones are buried even less deep, and so forth. The world looks normal. Here are all the freak worlds. The freak worlds are worlds where you can live. They're perfectly okay for living, but they have very strange freak things about them. History does not seem consistent. For example, in the freak world, you might find that all of the planets have solid gold interiors. Now, you can live on a planet with a solid gold interior, no problem. But how did you get there? How did you get there? What history could have left you through a solid gold interior? Well, the answer is just take that state with a solid gold interior, run it backward in time, and whatever you get back to, if you started there and ran it forward, you would get to the solid gold. And there's much more entropy, much more statistical weight in the freak universes. Much more. By huge, huge amounts. Okay, now let's start at I. I stands for inflation now, not for eigenvector. I stands for inflation. Here's the ordinary inflation starting point. And let's follow a phase space trajectory. And I'm thinking fairly classically, but I don't think that matters. We follow a phase space trajectory from here, and it goes through us, just the way we expect it to do. And then it keeps going, and it goes, and it goes, and it goes, and it goes. It's ergodic, or at least I'll assume it's ergodic. and it goes to every point multiple times, here and there and here and there. How many times does it pass through the freak universes? Many, many more times than it passes through the us universes, and vastly more, either of them, vastly more than the trajectory passes through I. I has a very small entropy. And so, what you can say, two very peculiar features of this picture. First of all, the trajectory goes from us to I just as frequently as it goes from I to us. I is not a pronoun. Us is. The trajectory goes from us to I as often as it goes from I to us. That's a little bit peculiar, but true. But more important, freaks statistically dominate by a huge, huge, overwhelming factor. So if you're interested in the statistics of the landscape and the statistics of the things that take place on the landscape and the statistics of different kinds of environments, freaks win by a vast, vast majority.
How is a freak defined? I mean, no,
something that you would ordinarily say takes an impossibly unlikely event to take place.
Like us.
No, we have a history that, no, we are not unlikely. No, it depends on what your definition. If you start with inflation, we have a story that makes a lot of sense. The universe evolved in a certain way, and then a little bit of chemistry created something, and it went on and on and on. It's not that unlikely. But a world in which every planet has a solid gold interior, I would say you would probably say there's no reasonable history that can get to it. But it's not true.
But to arrive at us, there are all kinds of relations among the fundamental constants, right? That
I'm not talking about
fundamental constants. Among the parameters of the theory, the masses and all of that. You know that. So
I refer you to Boltzmann. I refer you to Boltzmann, and I'll refer you to literature on this. This is Boltzmann and Claiborne, Dyson, and myself from 10 years ago. So this should be common knowledge. Okay. Well, it sure as hell should be. I think it is. Everybody knows this is Boltzmann brain problem, and this is just another way of Boltzmann. It's also the arrow of time problem. It's the same as the arrow of time problem. So let's say, what is necessary to get out of this? What's necessary to get out of this loop was suggested, I think a lot of people knew it. Raphael really wrote it down in the clearest version of it, and pointed out the importance of terminals. Now here is what he said. The terminals occupy a very small little comment in the paper. But what he says is there's no necessity for having a low entropy starting point. For example, you might start over here. The in now, IN stands for in, initial, stands for initial. I've used the same letter for a lot of things. Starts for initial. Suppose you start over here. This is a fairly low cosmological constant, a rather large entropy. It could have even been down here. It could have been even lower than us. Okay? What Raphael points out is that on the basis of ordinary statistical mechanics, if you're willing to wait these very long times, there will be up transitions as well as down transitions. So eventually, starting in this low entropy, a large entropy state, you will make a jump to a low entropy state, and from there everything will be normal, more or less as we know it. And eventually we may get to us. Now the problem is that if this was the whole landscape over here, we would run into Boltzmann's problem. Up transitions, down transitions, and we'd run into the same problem. What lets you get out of the problem is the existence of terminal vacua. Terminal vacua are either zero or negative cosmological constant that cannot reprocess, that cannot upjump anymore, that sort of end things. How do they end it? Well, they simply give you a way out of the box. A way out of the box. And if the way out of the box, if the rate for getting out of the box is faster than the rates for jumping up and down and so forth, in particular, if it's faster than the time necessary for freaks to happen, then you'll have a kind of flow. And the flow will not involve reprocessing and going back up and down and establishing an equilibrium, a time-symmetric equilibrium. This is what we need, is a flow from some starting point which exits through terminals in a time scale short enough that freaks are,
But how does this explain the arrow of time if you're still in just one path? You still have a problem with the arrow of time. You're just sitting in one minute.
No, if there's an overall sense of flow, let me give you an analogy. An analogy is a river. You have a river, and in the river, when the river flows downstream, all sorts of interesting dissipative structures can form. A rock in the river can cause eddy currents, cause eddies and vortices to form, which then flow downstream. Those eddies are recognizable, we know how they work, and they have a particular characteristic structure. Now compare that with another situation. The other situation is the river is completely stagnant. It's not static, it fluctuates. There are thermal fluctuations, and every once in a while the thermal fluctuation can create some kind of motion. Right? What's the likelihood that it will create a freak vortex instead of the kind of vortex that you're used to thinking about when the river flows downstream? I'm not sure what kind of vortex, but something that just doesn't look right. Something, a little vortex that makes a face or whatever. The answer is it's much higher than the sum total probability of creating freak vortices is much higher than the probability of making one of those nice recognizable vortices. The nice recognizable vortices had a low entropy starting point, and their probability was governed by the probability that you started in the low entropy starting point. The freaks, they can just happen as thermal fluctuations. You got to get out of the stagnant situation where there is no sense of flow. I'm going to show you one way, and it's the only way that I know, to escape from the stagnancy of the equilibrium eigenvector. And that has to do with terminal vacua. I've made a cartoon of terminal vacua. I've chosen vacuums which have zero cosmological constant. I don't quite know how to draw one which has negative cosmological constant. So let's concentrate on those. We're not going to use that in any way. But the thing that terminals do is they fractalize the inflating region. They no longer inflate, and so if you follow time, the creation of these terminals will create for the future time a fractal. A fractal in the sense that the inflating part of this region will not grow as fast as it would have originally. It grows with an anomalous dimension. The anomalous dimension can be thought of as the fractal dimension of the leftover stuff here. You can also think of it as a kind of statistical Cantor set. Every time you chop out a piece here, in one time interval, you chop out a piece. In the next time interval, you chop out smaller pieces. Next time interval, you chop out in a scale invariant way. That forms what you could call a statistical Cantor set, and what's left over, that's the inflating region, is a fractal, or a statistical fractal. How do you represent this on the tree? It's very easy. You just say that when n comes in, there is a probability gamma n for making a transition not to another de Sitter vacuum, but to a terminal. You prune the tree. You just chop off the branch. Now, there may be interesting things happening in there, but in calculating the statistics of this tree, terminals are just lopping off of branches. And you lop off a branch with a probability gamma n. Gamma n can be thought of as the total probability that n comes in and produces a dead branch. Doesn't matter which dead branch, you sum them all up. How does this affect the rate equations? Let's go back and redo everything we did before, but I'll try to do it a little faster. Oh, the index m, n, and m will stand for non-terminal vacua. It will not stand for terminal. The terminals we'll just get rid of. We don't even have to think about them. The analysis is similar to before. The rate equation is exactly the same, with the exception that there's one more term. This is the term, this is not summed on M, this is just M, no sum. This is the probability that you were in vacuum M at time U, and you made a transition to a terminal. So there's one more term in the rate equation. Detailed balance, I still assume, some detailed balance that the gammas are related to a symmetric matrix. And the definition of the rate transfer matrix gamma is the same as before. And in fact, the transfer matrix S is symmetric. From that, it follows that everything that I said before is still true. Nothing different. This introduces another diagonal term, so it's symmetric. The only non-symmetric term is this. The similarity transformation symmetrizes it, and there is still an orthonormal collection of eigenvectors and eigenvalues. So there's absolutely no difference until you come to ask what the eigenvalues are. Now, the largest eigenvalue is no longer 1. The eigenvalue is less than 1. It simply represents the fact that you leak out probability. The probabilities are not conserved. You leak out probability into the terminals. Okay. The largest eigenvalue is now less than 1. Now, if the rates are small, then they're very close to 1. If all the rates are small, then the eigenvalues are still very close to 1, but all of them, in fact. But the dominant eigenvector, this is the one of largest eigenvalue, is less than 1. This should read 1. Lambda d is less than 1. Eigenvalue less than 1. And the dimension that's associated with it, the logarithm of lambda, is greater than 0. That's the first message, that there's no dimension 0 eigenvector. This doesn't exist anymore. Everything exponentially decays. Let's look at the one-point function. Well, okay, here's the dominant eigenvalue is associated with a dominant eigenvector. The dominant eigenvector I'll call d sub m. This is replacing O sub m. It now has time dependence, and it falls like e to the minus, or 2 to the minus lambda d times u, times a thing which doesn't depend on time. All right, this is just a time dependence from the rate equation. The probability in the attractor state D, the dominant state, D is the dominant state, the one of largest eigenvalue. It's the one that's left over after all transients have disappeared. After all transients have disappeared, the dominant eigenvector takes over, and here's what it is in terms of probabilities. Just like before, except now this is dominant instead of O. That's really the only big difference between the two cases. Okay, let's, first of all, there's the one-point function. The one-point function is just that probability piece of D. Let's go after the two-point function. And it's time dependent now. It falls off like 2 to the minus lambda D. Let's take the two-point function. The two-point function, everything is exactly the same, no difference, up to some point. All right? In particular, the probability for the initial state R is not e to the SR anymore. It's e to the SR times dr, dominant eigenvector, dr. The dominant eigenvector is not approximately equal to the equilibrium eigenvector. They're quite different. They're dominated by different physics. dr is very often very, very different than the equilibrium eigenvector due to the leakage of probability into the other case. All right? And it's time dependent. So here it is. The two-point function is the same as before. It has a probability for R. It has a pair of propagators. You go through it. Here it is. The only difference, now you probably won't remember, but when I did it before, the dr canceled against the e to the minus sr. It left no r dependence except for I and j. When summed over r, this gave you diagonality of the two-point function in the conformal, in the scaling basis. Now what happens is different. It looks like 1 over x minus y the delta I plus delta J minus, sorry, this is plus delta D plus the dominant eigenvector. What's going on here looks very much like a 3-point function. Notice that this is the kind of thing that went into the structure constant of a 3-point function. In fact, it is the structure constant of something that looks almost like a 3-point function. This thing here is the correlation function, sort of some kind of it's not a 3-point function. What it actually corresponds to is a 3-point function with 1 point moved off to infinity. There's an insertion, an extra insertion of a dominant eigenvector. It looks like a background. I don't believe there's any conformal field theory for which this is the correlation function. In fact, if you work out the cluster decomposition, since there's no unit operator anymore, there is no clustering. Instead of cluster decomposition, the closest you have is a leading piece which is gotten by inserting the dominant eigenvector.
So it's a little like spontaneously broken conformal symmetry.
I think it's not at all like spontaneously broken conformal symmetry. I don't know.
Sort of like the ground state no longer has...
Yes. But in any kind of field theory, whether it's broken or not, there's always a unit operator. Here there's no unit. This doesn't cluster. It violates cluster decomposition. It has its own kind of cluster decomposition. It is not scale invariant, but scale covariant. Notice that everything comes, what did I write here? There should be a plus delta. I was getting tired by the time I wrote this. There should be a delta D here. A delta D, the insertion of D. Not diagonal. Contains an extra delta D there. And it's not a conformal field theory correlator. It's just not a field theory correlator altogether, but it has a very definite structure. More or less as though you put an extra operator into every correlation function, one extra operator. Not diagonal. It's translation invariant, rotation invariant, scale covariant. You can define it in a way that makes it scale invariant. And it's an attractor. It's an attractor that everything will flow to in enough time if we have these very large times. Let's come back to the causal patch view. Everything is exactly the same as before. The probability, to begin with, the probability that you get the vacuum N starting at M after one jump is still gamma Mn. But if you use the Bayesian analysis again, you'll find out that because the probabilities are not governed by the equilibrium probability distribution, things don't cancel in the same way, and the ratio of probabilities forward and backward is simply not 1. Now, it would be very nice if I could come and tell you, okay, the ratio of probabilities is exactly right to describe a universe in which planets are iron and not gold. I'm not even going to try to get there. I'm simply going to say this is the evidence that this system has an arrow of time. It has an arrow of time. The arrow of time does tell you that the future is different than the past. I'm going to leave it at that and not try to do phenomenology with this. Premature, I would say. Okay, let's see. Where are we? What happened here? Oh, what happened? We're not playing, are we? Play. I'm actually just about finished, but my technological... I'm not even sure. What do I press here? I never had a laptop. I don't even know what to press. I wanted to go to play. Oh, okay. Yeah, hold on. I had another slide there. Okay, I know what the other slide said. The other slide was just a lesson. It was a big lesson. What is the lesson? The lesson is that conformal symmetry is intimately connected with the lack of an arrow of time. That conformal symmetry is a thing to be avoided if you want to understand why time goes one way. And that you need a mechanism to break the conformal symmetry. But the breaking of the conformal symmetry is not of the kind that an ordinary flow to a conformal fixed point would correspond to, that will have the problem that the infinite future is dominated by Boltzmann's nightmare. It doesn't matter if you start someplace else and you flow to a conformal field theory, you still have Boltzmann's nightmare. You have to have this ongoing, continuing depletion of probability out into terminals to create an arrow of time in this long time interval sense. That is, I think that pretty much covers what I wanted to say, at least this morning. This afternoon, if we have a little time, I would go on and show you some ways in which you can recognize from this tree picture some of the things that people like Busso and Guth and their collaborators, Freivogel, have argued about measures. Turns out this is a nice vehicle, not for explaining why the measure has to be a particular thing, but seeing the machinery and the mechanics of the little calculations they do, and to see how it, if we believe those calculations, not if we believe the calculations are right, if we believe the logic, how it influences the cosmological constant, how it influences the question of the conspiracy, what's it called? The coincidence problem. Yeah. And then that's enough. That'll be enough for today. Okay, so I'm happy to take questions now.
But does this solve the measure problem?
No. Okay. This certainly was.
You had this cutoff.
Yeah. I'm going to use that cutoff, and I'm going to say with that cutoff, and I'll tell you which of the many cutoffs that people have proposed it corresponds to. But yes, and this is a light cone cutoff of Busso. But it certainly doesn't tell you in any a priori fundamental foundational sense why that's the right thing to do. I think to know why that is or isn't the right thing to do, we have to get into a deeper, much deeper story. Notice, nothing I said was quantum mechanical, other than the statement that there are rates of transition. This was an entirely classical stochastic description of things. Whether quantum mechanics is appropriate on scales bigger than a horizon size, I don't know. But I certainly didn't really use it. I assumed that you could explain what I wanted to explain by classical stochastic reasoning. So in that sense, I'm pretty much just using this as a tool to understand things that people have said up till now. It's a nice solvable model where you can see the various things happening. Whether it in any sense corresponds to a deep a priori foundational explanation of anything, no, I don't think it does. That I think needs something deeper.
Second question? Oh, here's
yeah, we have time.
In the picture that you had to illustrate the Boltzmann brane problem, where you're much more likely to get to our universe starting from a freak. So now you put a hole in the wall of the box so trajectories can go out.
And if they can get out on a time scale short by the time that they would find freak universes, then you're in business.
See, but you still might worry that we're more likely to get to our universe from a freak than from some sense.
You might. Then it becomes a quantitative question. Good. Then it becomes a quantitative question. The quantitative aspects of it have been discussed by Busso in particular. I was less interested in the quantitative aspects of it than I was just in exhibiting what it takes to make a overall robust. Now, fluctuations can lead to arrows of time, but they're sort of localized arrows of time. For some period, there'll be an arrow of time that goes this way, and then later time, the arrow of time will go that way, and it will fluctuate endlessly, with spending most of the time with no arrow of time at all. With terminals, there's a robust arrow of time, but it's a question of its strength. Let's go back to the river for a minute. If the river is moving too slowly, it may still be that things are dominated by fluctuations rather than by sensible vortex eddy emission. So there comes a quantitative question. The quantitative question is the flow strong enough, and is it strong enough everywhere on the landscape to overwhelm the possibility that you'll be dominated by freaks. That becomes quantitative, and that I can't answer. That was not the goal of this exercise. Good.
Lenny, I had a technical question, and then perhaps a comment.
Good.
The technical question was, in your models, your valency for your graph is always P.
Yeah.
Now, if you had a mixture of different P's,
that's a good question.
Mess up the mathematics?
I don't know. That's a nice question. First of all, I don't think it messes up the mathematics if we replace P by N. You know, where N is not prime.
No,
yeah, right. It doesn't mess up it does mess up the particular structure of the group that I wrote down, but that's not important. So the question is, if there was a statistical distribution of different valencies,
exactly.
What would that do? I don't know.
Its amplitudes go from one universe.
For some odd reason, I never thought about that, but it's a very good question. I don't know.
And the other comment or question is, the image you paint is of a drunkard's walk, except eventually alcohol takes over and poisons the drunk. Or as Keynes would say, in the long run, we're all dead.
Yeah, but we're all dead, but there's always new ones coming.
Yeah.
There's always new ones coming.
We don't worry about it.
There's an interesting paradox, which goes back to some things that Busso said. Let's suppose there is an origin to the whole thing, an initial state. The initial state could just be one of the many points in the landscape, just as a model, not to be taken seriously. Then if we just thought in strictly causal patch local language, we would say we now are probably within a couple of hundred transitions from the initial state. I'm assuming the landscape is 10 to the 500 or something. How many transitions would it take to get to a terminal? The answer would be a couple of hundred, so we're probably within a couple of hundred, and certainly not enough time to have established the dominant eigenvector. On the other hand, if we take into account that there's this growing bush of things, and we think of statistics in the purely frequentist way, we count how many of each kind are there, we'll find that it's dominated by late times, and the late times have had more than enough time to equilibrate. So it's a kind of paradoxical, which way should you think? Should you think you're part of this enormous ensemble? Now what Raphael points out is that the local and global picture are exactly the same if you take as your initial condition the dominant eigenvector. If you take as the initial condition the dominant eigenvector, then you can think locally or you can think globally and you get the same answer. But if you ask why did we get to the dominant, why do we use the dominant eigenvector, the answer has to be that we take seriously the more global picture.
See, the dominant eigenvector is the same as the Hartle-Hawking wave function, right? It's the
No. The equilibrium eigenvector is the Hartle-Hawking.
Sorry, the equilibrium.
Yeah. And I'm not saying the Hartle-Hawking thing is not a good thing. I think it's a good thing, but it's not. You're welcome.
By equilibrium, you mean the conformal one?
Yeah.
You're saying it can't capture non-conformal physics? It can't capture the decayed terminals? I mean, why is it not?
No. It's a different equation. The equation without the extra gamma in, that gives you the Hartle-Hawking. With the extra gamma in, the statistics is completely different. And instead of being dominated by the thing of smallest cosmological constant, it tends to be dominated by the thing of longest lifetime. So Hartle-Hawking doesn't depend on the rates, the equilibrium distribution. It's just e to the s. The dominant eigenvector very definitely depends on the rates. Now, if the rate to terminals is very much smaller than all the other rates, then the dominant will look like, but in general that won't be the case. In general that won't be the case, and there will be sort of significant differences between the two. Right. Well?
I mean, you have a boundary, don't you? And one way to think about it is Brownian motion with an absorbing boundary.
Yeah, absolutely. And a source that keeps repopulating.
So it's not the no boundary proposal, it's a boundary somewhere proposal.
So what I just want to say about that is really, if you have enough time to establish the dominance of the attractor, then it doesn't matter where you begin. Wherever you begin, you will get to the attractor.
Okay, so I just don't want to misunderstand you. So the correlators that you computed, am I to conclude from that if you want a holographic theory of this eternal inflation with an arrow of time, it's got to be some weird non-conformal...
I don't even think it's a field theory. All right, look, one of the things I came here to ask people is, have you ever seen a structure like this before? What is it? What kind of structure, if it's not a conformal field theory, and I don't even think it's a field theory, what is it? Has it ever been seen in statistical mechanics before? Is it something that is recognizable? And so far, I have not gotten any answer. So it may just be something new. But it exists. It exists in the sense that in this completely solvable model, that's the answer. That's the advantage of models sometimes, that you can... Well, thank you for listening.